So, wonderful, good afternoon, good evening, or good morning, depending wherever you are, and welcome to this talk about the solid principles. Allow me to introduce myself first. My name is Klaus. I'm a C++ trainer since approximately 2016. Additionally, I also do C++ in my free time. So I'm, for instance, the author of a C++ library called Blaze. And I'm one of the organizers of the Munich C++ user group, which, as a side remark, may be one of the biggest and most active C++ user groups worldwide. Today in this talk, we're talking about software. And as this may not come as a surprise, because probably all talks at this conference are about software, this is really about software. There is a reason that software is called software, because we have a certain expectation in software. The soft actually means that it's easy to change and easy to extend. That was initially the reason why software was called software in comparison to hardware, which is difficult to change. However, unfortunately, you may have experienced this yourself, it may not be true that software is easy to change. So it may depend on where you work, but especially larger frameworks tend to be harder to change, harder to extend. And that ultimately may be due to dependencies. So perhaps to quote David Thomas and Andrew Hunt on this one, coupling is the enemy of change because it links together things that must change in parallel. And a second expert, Ken Beck, said dependency is the key problem in software development at all scales. So dependency coupling, as another word, is exactly the problem that we need to overcome in order to write large-scale software. Unfortunately, this is not an easy problem. On the contrary, this is a particularly difficult problem, but luckily there is a couple of guidelines that help us. And this is exactly what this talk is about. This is about the solid principles, a set of guidelines that allows us to deal with dependencies in different ways. So behind these solid acronyms, there is 5 principles. The first one is called the single responsibility principle. As this name already suggests quite a bit, this is probably one of the most misinterpreted principles, and definitely we have to talk about this in detail. The second one is called the open-close principle. This name does not suggest a lot, but believe it or not, this is actually one of the most important principles that I can tell you. Then comes the iskov substitution principle, much wider known. And even if you don't know this and haven't heard about this before, you will definitely use this on a daily basis, I assume. The I is the interface segregation principle. This name again suggests a lot. So it's about segregating interfaces. We talk about why and how. And the last one is the so-called dependency inversion principle. Now allow me 1 or 2 sentences about the history of these principles. They are not particularly new. So for instance, the open-close principle and the iskov substitution principle have been formulated in 1988. But only in the year 2000, the left of these gentlemen, Robert Martin, he actually selected these 5 principles as the most important software design principles. At that time, he selected them as the most important object-oriented design principles. We're going to talk about that too. A couple of years later only, Michael Feathers realized that if you arrange these 5 principles in exactly this order, then the first letters give you solid. And this is when officially these solid principles were born as a very, very important set of guidelines to write clean code. Now in Wikipedia, solid is mentioned as well. However, you might see this, it's a little small, but this is about object-oriented design. In this talk, I'm trying to do this a little differently. So in this talk, I will introduce the solid principles as a set of guidelines not limited to object-oriented programming alone. I will try to introduce them as a general set of guidelines for object-oriented programming, functional programming, generic programming, and basically for all the languages that you might be using. So in other words, I try to introduce them as a universal set of design guidelines. Now, I will do them in order, and the very first of these principles is the single responsibility principle. If you wouldn't have heard about this principle before, I believe you would first of all go to Wikipedia and try to get a first idea what this principle is about. So this is what Wikipedia has to say about this principle. The single responsibility principle states that every module or class should have a responsibility over a single part of the functionality provided by the software. And that responsibility should be entirely encapsulated by the class, module, or function. All its services should be narrowly aligned with that responsibility. Whereas this may sound pretty nice, pretty reasonable and intuitive, I believe there's a lot of questions in there, especially the question about responsibility. What is the responsibility? So in other words, what should my class, module, or function should have only one of? This is a seriously difficult question. And unfortunately, this principle, therefore, has been simplified and perhaps to some extent distorted into something like that. Everything should do just one thing. That is what I would call the common knowledge. Although this may sound simpler, it's probably even more vague. Should do just one thing. What is this one thing? Really hard to answer. And so I was looking for a better explanation of what SRP is truly about, how we can understand the single responsibility principle. And I found a quote in a book called The Pragmatic Programmer. These two guys, Andrew Hunt and David Thomas, do not talk about the single responsibility principle. They actually talk about orthogonality. We want to design components that are self-contained, independent, and with a single, well-defined purpose. They use the word cohesion here. When components are isolated from one another, you know that you can change one without having to worry about the rest. So I have to admit, I like this quote much better because it basically gives us an idea that this is about change. We truly want to change easily. And they do not use the word responsibility, but purpose and this other word, cohesion. And I believe together with a quote from Tom DeMarco, the idea of the single responsibility principle becomes clear. Cohesion is a measure of the strength of association of the elements inside a module. A highly cohesive module is a collection of statements and data items that should be treated as a whole because they are so closely related. Any attempt to divide them up would only result in increased coupling and decreased readability. So ultimately, of course, our idea is to decrease coupling, to increase the coherence of things. So the single responsibility principle is not about doing one thing, which is really way too vague. It's about the structure of code. Those things that truly belong together, that you cannot separate intuitively, those things should go together. But everything that does not belong, everything that is an orthogonal aspect, a separate aspect, should be separated into a different software unit. This could be a different function, a different class, a different module altogether. But it definitely should be separated from this other orthogonal aspect. So Robert Martin, the one who put these solid principles together, simply said, a class should only have one reason to change. So indeed, ultimately, it's about changing things easily, changing things in isolation. So how does this work? Allow me to give you an example. A circle class. Okay. I know a circle class may not be what you expect as a realistic, bigger example, but we tend to understand circles and other kinds of shapes pretty easily. And let's face it, it's kind of tradition to introduce things by means of some circle or animal hierarchy, or shape or animal hierarchy. So let's deal with a circle here. This circle, first of all, gets a radius, which it gives to a data member, and there may be some other data members, like some center position, some orientation, whatever we need. There may be a couple of getters that allow us access to this, to all these data members. Then we can translate a circle, meaning move the center point to another position. Of course, we can rotate it. Everything needs a rotate, of course. And then it can be drawn to the screen, drawn to the printer, and it can be serialized to some byte stream. Of course, this class is not perfect with regard to the single responsibility principle. It may sound like a amazing idea to actually put everything that a circle ever can do inside the circle, to give a user the ability to draw, to serialize, and do whatnot. But it's not necessarily a good idea from a coupling point of view. So my problem is primarily these three functions and potentially all the functions that are not visible. These three functions make it harder to deal with a circle in general. These three functions make it hard to change the circle. So let's think about, when does a circle change? When do I have to go to the circle class and make changes? Well, first of all, I probably have to do changes if some basic properties of the circle change. Well, this may, of course, be if we decide that a radius is not what we need, we want to use the diameter instead. I think this is a fairly rare case, but still, it's a possibility. This circle also changes if the screen class changes. Then we have to go back to the draw function and adapt the function accordingly. And of course, the same is true for the printer class. If printer changes, we adapt something in circle. And of course, it also is true for byte stream. The circle also changes if the implementation details of draw change. So if we decide that we do not want to draw by means of OpenGL anymore, but that we want to use something more modern, like metal or Vulkan, then we are changing the circle class. And of course, the same also holds true for all the other functions. For instance, serialize. Serialize may change if we decide that we don't want to use big endian, but little endian. And so implementation details of circle would change. And of course, there may be many, many more reasons why I have to go back and change circle. Ultimately, this is exactly what we do not want to have. And just for the single reason of not introducing too many dependencies. If you visualize these dependencies, then this may look something like that. So there is a circle class, and it comes along with its brother square. And both circle and square are aware of screens and printers and the byte stream also. Now imagine that eventually I want to compute overlaps between different kinds of shapes. So this is an entire module with functionality just for that purpose. Computing the overlap between circles and square has nothing to do with screens, printers, and byte streams. Yet still, overlap knows about them due to this hidden dependency. And that, of course, is unfortunate because every time I add up something in screen, there is the danger of a change in overlap too, etc., etc. This kind of dependency is exactly what makes it so hard to deal with things. This is what makes it so hard to change things in isolation. A much better approach would be to handle things in this way. So overlap simply knows only about circle and square. And you might imagine some module that deals with drawing. And that module, of course, also knows about circle and squares, but also about the screen. Printing would additionally need the printer, serialization might need the byte stream. Everything is much easier. Also, it's much more honest about the dependencies. There's no hidden dependencies, things that make my life harder. So ultimately, indeed, these three functions, draw, so the to draw and serialize, should not be part of the circle in order to minimize dependencies. A couple of further examples. So for instance, the design of the STL very, very nicely follows the single responsibility principle. Data structures, algorithms, allocators, very nicely separated. Of course, they share a common interface, such like iterators, but they don't have to know about each other. I can change one without having to worry about the rest. Very nice example. Also, I would argue standard vector follows the single responsibility principle nicely, because all of the functions are truly focused on managing a dynamic array. Standard string, on the other hand, does not perfectly follow the single responsibility principle. Standard string does not come just with the functions that vector provides, but it comes with a myriad of additional functions, set of additional functions that can virtually do anything to a string. So there is find functions, there is replace functions, there is substring functions, a lot of functions that actually could be represented differently. And today we know they are. Historically, string is just older than standard vector. It was not part of the STL initially. So string is the counterexample of what we should do. The vector is the example of what we should do today. But of course, the single responsibility principle also is applicable to functions themselves. So imagine, for instance, this withdraw money function that is implemented as a member function of bank account. So if you want to withdraw money, then first of all, you should verify the access of a given user. Is this user actually allowed to withdraw money from this account? Then probably you have to verify the balance in the account and of course update the amount accordingly. If this function would be implementing all of these aspects, these orthogonal aspects itself, it would clearly violate the single responsibility principle. It would be very, very hard to deal with all of these aspects in just a single function. Not a good idea. And also, of course, I would have to change this function for many, many different reasons. If, however, this function would just call other functions, so forward requests to something like verify access, verify balance, and update balance, this actually would follow the single responsibility principle. And it would give us the opportunity to separate even more. Verify access does not have to be a function in this particular class. It is a completely orthogonal aspect in itself, so perhaps a different class or a completely different module would be even better. So this function does one thing, it brings together all of these three aspects. But it's a very, very hard argument to make. So primarily think about changing. When would this function change? And I would argue it would change if the general algorithm how to withdraw money changes. And for that reason, it does one thing. So as a takeaway, prefer cohesive software entities. Everything that does not strictly belong together should be separated. And that ultimately is the single responsibility principle. I know it is hard to apply in practice, and it's also pretty hard to reason about things. But my experience is, if you face a problem in changing things, then very, very often SRP is indeed violated in some regard, and it helps to separate concerns. So, of course, I'm very happy to answer questions. My suggestion is that you just post them in the Q&A section, and I'll try to answer as many questions as possible in the end. That would probably work pretty well. Please note the slide numbers. This would definitely help to go to back to specific slides. All right, after having handled the single responsibility principle, let's talk about the second one, the open-closed principle. That name, unfortunately, does not give away a lot, but still, it can be intuitively explained. So in 1988, Bertrand Meyer argued that software artifacts, classes, modules, functions, etc., should be open for extension, but closed for modification. So what he has in mind is that at any point, you should be able to extend software, to add new functionality, but at the time you're doing this, you should not have to change existing software. So in a perfect sense, you just write new code and don't have to touch old code. Let's take a look at a slightly longer example. This time we truly want to draw different kinds of shapes. And I start with a procedural approach, something that you definitely have seen before, something that reminds you a little bit about good old C programming. So in other words, I start with a good old enumeration type. It's called shape type. And at this point, it tells us that there are circles and squares. Apparently, there's only these two, but of course, we will later think ahead and try to add new things. Then there is a base class called shape. The curious thing about this shape base class, and it indeed is a base class, it's a virtual destructor, is that it in the constructor takes one of these enumerators and stores it as a data member. So in other words, this shape remembers what it truly is, a circle or a square. And this is, for instance, used to define a circle. The circle class publicly derives from shape, and for that reason, of course, has to call the constructor of shape by initializing this shape. Well, it's a circle, so I should use the circle enumerator. I should remember that I'm a circle. So it has a radius, of course, a couple of other data members, as we've argued before, a couple of getters also. And additionally, it has the necessary functionality. So I can translate circles, I can rotate them, and of course, I can also draw circles. Note that I'm actually now choosing the free function approach. So draw is no longer part of the circle, it's extracted in order not to couple the drawing aspect strongly to a circle. So then I mentioned the brother of circle before, square. Square is also shape, but the primary difference is that it initializes the base class with a square enumerator. So the square, of course, remembers that it is a square. Else, it's probably exactly the same thing, pretty much a copy and paste issue, but it also comes with a set of functions that deals with squares. Now, I, for instance, want not just to draw single shapes, I would like to draw a whole bunch of shapes. For instance, I would like to draw all the shapes that are part of a vector. So as an argument, I get a vector of shape pointers, and I want to draw all of them. So first of all, of course, I'm traversing all these shapes. And now I have to ask what they truly are. So it's just a shape pointer. I have to figure out what it truly is. So I'm asking for the type, for the enumerator, and I switch. Is it a circle? Well, if it is a circle, then I have to cast to circle pointer and call the according draw function. Else, if it is a square, then I cast to square pointer and of course call the according draw function. This works. This is easily proven by just creating a couple of shapes, so a circle, a square, and a second circle, pushing them into a vector of shape pointers and drawing them all. It indeed works. I see something on the screen. However, so first of all, I go back to these translate, rotate, and draw functions. At this point, you might be thinking, oh my, this is old, this is so bad. There is one aspect about this code that is actually positive, and this is very interesting. This code actually fulfills the open-close principle in terms of functions. I can add new operations if I just follow the example of adding free functions. Nobody can hinder me to write an according free function, and of course, even third-party people, people that use this as a library can add new functionality by introducing a new free function. And since this is chosen by this library as well, it feels kind of natural and intuitive. In this regard, it actually fulfills OCP. But, okay, I should mention that I talked about this particular aspect in a talk at CppCon 2017, talk called Freer Functions. It was primarily focused on explaining that free functions have a design advantage in many, many aspects. The open-close principle was just one of them. However, of course, and this is what you would complain about, this idea, this design fails if we want to add new types. So just as a thought experiment, let's add a rectangle. So I extend the enumeration, add a new enumerator, and this change is visible. For instance, in circle, because circle knows about this enumeration. It is also visible in square. And for that reason, circle and square both have to recompile. Things may change. The underlying size of the data member might change, possibly. And of course, I have to add a new case statement. The case statement itself is actually not the problem. It's pretty easy to put into this code to get it right. Suddenly I can draw rectangles. That's fine. The bigger issue is that everywhere where I switch based on a type, in all the places where I have a switch statement, an if, else if cascade, or anything similar, I now have to change code. And in the bigger framework, this may actually be dozens or even hundreds of places. And how do I find all of these places? How do I actually get a guarantee, or do I get a guarantee that I found all the places that I need to change? Probably no. And so this is a nightmare situation, a situation that really makes the difference between adding things easily and very, very difficultly. So Scott Myers said about this, that this kind of type-based programming has a long history in C. And one of the things we know about it is that it yields programs that are essentially unmaintainable. So this, in terms of adding types, is not a particularly good design. And of course, you're thinking, why don't we add? Yes, of course, a couple of virtual functions. So if you redesign this entire thing and use an object-oriented approach, we would define a base class that has a couple of virtual functions instead. No enumeration anymore, no data member anymore. This now is a true interface class, protocol class, in the sense that it only has virtual functions. So the structure and a virtual translate, rotate, and draw function. Everything that derives from this class now has to implement these functions. So for instance, circle. There's no need to initialize the base class anymore. No initialization required, but of course, I now have to implement these functions. And the same is true for every class, so also for square, every class deriving from shape, I also have to implement these functions for square. Of course, this is the functions that before I'd implemented as 3 functions. They have just moved into the class. The draw function now suddenly becomes something very, very easy to change, very easy to adapt. In fact, I probably will never go back and change or adapt it, because this function now very, very nicely fulfills this open-close principle with regard to types. It is completely oblivious of any kind of shape type, no concrete type, anything can be drawn. And this still works with exactly the same main function as before. So still create a circle, a square, and a second circle, and we'll just draw the thing as before. So the decisive thing is that we have now switched to virtual functions. This makes it easy to add new types. New types are simply added to the code. I do not have to go back and change other pieces of code. However, if you want to watch closely, then you do realize that I have another problem now. I'm back to having the draw function inside the shapes. And by that, of course, I'm coupling the implementation details of drawing. And of course, by that, I actually no longer adhere to the single responsibility principle. So if you have not seen this problem before, if you have not seen this contradiction between SRP and OCP, then you have not been involved in a discussion that is currently ongoing. Is this truly the right approach for general purpose programming? So indeed, in the community, there is a discussion of whether we can do things better. I talked about this in detail at a talk in Bucharest in February. The talk was called Embrace No Paradigm Programming. In this talk, I compared 7, and yes, in 60 minutes, 7 different approaches to drawing shapes. And of course, I compared the 2 solutions that we've seen so far, but also modern C++ patterns, like, for instance, variant approaches, type-erased approaches, etc. The conclusion is indeed that the modern approaches are better. One of the takeaways for you is, indeed, I have to choose in dynamic memory, in dynamic polymorphism, between the 2 different versions or facets of OCP, adding operations or adding types. You will probably, as long as you want to be dynamic, not achieve both. If this is something that you're interested in, I recommend a talk, one of the first talks on Wednesday, given by Cy Brandt, Dynamic Polymorphism with Code Injection and Meta Classes. This code will explain why we are, to some extent, moving away from these virtual functions, how we can actually make extending things easier, how we can bring SRP and OCP together. However, I should also show, at least briefly, that the open-close principle can, of course, also be applied to functions, not just classes or class hierarchies. I've chosen the copy function from the STL because copy is actually very, very great in terms of OCP. So the copy function works for all copyable types. It works for integers, strings, it works for U-types, and it also works for the types that you're writing tomorrow. It works because it basically provides you with a couple of concepts, named template parameters, And everything that adheres to these concepts just works. And I do not have to adapt this function for new types. No, as long as the types provide all the necessary operations, this function is actually closed for any kind of changes, for any kind of extension. This is a good design in general, so this works pretty well. So the takeaway is that you should prefer software design that allows the addition of types or operations without the need to modify existing code. Because only that makes your life truly easy. Only that will, in the long run, allow you to maintain the code for a long period. All right. So again, if you have questions, please post them. I will try to answer as many as possible in the end. Which brings us to the third principle, the Iskov substitution principle. The Iskov substitution principle, as the name suggests, is about substitutability. So in order to explain it, I, first of all, can show you the original statement of Barbara Iskov. What is wanted here is something like the following substitution property. If for each object O1 of type S, there is an object O2 of type T, such that for all programs P defined in terms of T, the behavior of P is unchanged when O1 is substituted for O2, then S is a subtype of T. So actually, this is very concrete and very accurate for a mathematician. However, for all the other people, a simplified form might be sufficient, although it's nowhere close to being as accurate as the first statement. The idea is that subtypes must be substitutable for their base types. Initially, you would think this is only for inheritance hierarchies. I will show you in an example later that this is not necessarily just about inheritance hierarchies. However, intuitively, it is about behavioral subtyping. This is what we simplified call an is-a relation. Behavioral subtyping means that I have an expectation on some type, and these expectations should be fulfilled either by some other concrete type, which fulfills some kind of template parameter, or by some deriving class that implements a base class. Behavioral subtyping includes that method arguments are contravariant, return types are covariant, that preconditions cannot be strengthened in a subtype, and postconditions cannot be weakened. If these four hold, it actually might work pretty well. And also there is something about invariance. The invariance of the supertype must be preserved in a subtype. So if I have some expectations, important expectations on the supertype, the subtype cannot break them. So again, I have a code example, which is definitely easier to understand than some theory slides. This is now a very common explanation or a common example for the Iskov substitution principle. In other words, you might actually have seen it before. So don't post anything to the chat. Do not give this away, because everybody who has not seen this before should get at least a couple of seconds to actually digest the problem and think about this. So the question is, which of the following two implementations would you choose? So there's two to choose from, and both implement an inheritance hierarchy. I admit I stick to shapes, and so option A is about a square and a rectangle. I start with a class called square. A square class, first of all, has a data member called width. A square has a width, and it comes with a virtual function that allows me to set the width. Additionally, I have a virtual getArea function, which, non-surprisingly, is implemented as return width times width. So I can actually get the width of a square quite nicely. There may be more functions, but this is the ones that are really interesting for us. This square class now serves as a base class for a class called rectangle. The rectangle class needs a second data member because a rectangle does not just have a width, it additionally has a height too. And so in addition, it also comes with an additional setter, the setHeight function. SetHeight sets the height, and of course setWidth continues to set the width. The getArea function is now not doing the right thing anymore, but it's a virtual function, so I can now write it, and I'll write it as return width times height. Now it's doing the right thing again, and everything works. This rectangle class, this deriving class, now extends the functionality of the base class. It adds new behavior, setHeight, and it adds a new data member. This is option A. On the right-hand side, we have option B, which is, to some extent, the inverse of this of solution A. I start with the rectangle class. And as we've said before, a rectangle needs two data members, width and height, and for that reason also has two setters, setWidth and setHeight. It again has a getArea function, which of course is implemented as return width times height. Again, there may be more functions, but this is what is interesting for our purposes. The square class now implements the rectangle class, so it publicly derives from rectangle. A square actually only has one side length, which means right now it has a little too much. It tries to restrict the interface of the base class by implementing or overriding both of these virtual setters. SetWidth is implemented to set both width and height, and also setHeight is implemented in setting both the width and the height. So this is how square actually fulfills its own invariant. It only has one side length. It's just sort twice. If I do that, if I do it this way, then getArea actually does the right thing. Width and height are always equal, so getArea will return the right area. I can optionally override it. I don't have to. So this is what I usually ask people in my training classes. And I make them choose which of these two is the right choice, which one they would choose. And a surprising large number of people choose option B. I would argue it's approximately 70%. There is always a couple of people that choose option A because they actually fear that option B is a trap, that something is not right. Also, they don't like the fact that a square has two data members. But the largest number of students choose option B. The surprise is big. If I explain them, then option B doesn't work. It doesn't work because actually it does not fulfill this iskov substitution principle. A square has to change both data members. So if I call setHeight, it has to change both. The surprise is big for a rectangle if you change one side length, call the area function, and find that the area is not what you expected. That two data members instead of just one changed. Well, the expectation in rectangle is that I can set the data members individually, which is no longer true in square. So this square does not behave like I would expect of this rectangle. So option B is a bad choice in inheritance hierarchy. And for that reason, for a long time was actually listed as a breaking or violation of the iskov substitution principle in Wikipedia. However, option A is unfortunately in no way better. It is exactly the same problem, just with a different twist. In case of a square, I expect it has one side length, which no longer is true with the rectangle. A rectangle certainly has two. And so again, if I set via the base class the width and call the area function with a certain expectation, it might not hold. So both versions do not adhere to the iskov substitution principle. The takeaway of this is not that inheritance generally is broken. The takeaway is that we are very, very easily misled. Especially the right version is natural and intuitive. In math, naively speaking, a square has this relationship to rectangle. But in computer science, this might not be true. It depends on the expectations in the base type. It depends on the interface. So if you inherit from some base type and there is expectations, make absolutely sure that you understand the requirements, that you understand the type, the contract on the base type. That is the one thing that the Iskov substitution principle tries to teach us. Exactly the same is true, however, for templates in general. I again chose the copy function because it again serves my purposes. It is about the two data members, input and output. Input it, output it. Everything that you pass to the copy function should behave like an input iterator and output operator respectively. So if you pass anything that does not behave as expected, so does not really do something reasonable with regard to increment or comparison, it just doesn't work. Also here you have expectations and these expectations must be fulfilled. So also here you can apply the Iskov substitution principle. So copy works if the given input iterator adheres to the required concept and of course also the output iterator adheres to the required output iterator concept. So the takeaway here is make sure that inheritance is about behavior, not about data. As soon as there's a virtual function that raises expectations, this is what inheritance truly is about. Make sure that the contract of base types is adhered to. If there are expectations, they need to be fulfilled, else the inheritance relationship might break in surprising and unexpected situations. And make sure to adhere to the required concepts in templated code. That is, to some extent, the equivalent of the base class idea. All right, this was the third of the solid principles. The fourth one is called the interface segregation principle. From my own personal point of view, this is indeed a special case of the first one, the single responsibility principle, but a very important case. Robert Martin states that clients should not be forced to depend on methods that they do not use. And Wikipedia probably even uses an easy explanation. Many client-specific interfaces are better than one general-purpose interface. So I again have an example. Let's remember that we started, or I should say ended, with a shape class that had virtual functions. The big problem now is that circles might contain implementation details of drawing, an aspect that might change frequently, where I perhaps even want to have several different kinds of implementations. So this probably is not flexible and extensible enough. For that reason, I now reach for a design pattern, namely the strategy design pattern. The strategy design pattern is one of the classic design patterns from the Gang of Four book. This is exactly copied from the book, but for our purposes, I now adapt the name such that we understand what's going on. So on the left-hand side, I have the shape hierarchy with the draw function. I want to extract the implementation details of draw, and I do this now by means of introducing another hierarchy, draw strategy. Shape owns one of these base classes, and of course, this here can have multiple different kinds of implementation. There can be an OpenGL strategy, a VTK strategy, a metal and Vulkan strategy, and of course also test strategies. This is one of these strategies is usually passed to the shape via the constructor or via some setters. This is what we call dependency injection. This allows me to extract the implementation details from shape. So if I transfer this in code intuitively, perhaps a little naively, I might now implement this in this form. I introduce a draw strategy, which comes with a virtual draw function for all the available shapes. So we had circles and squares in these examples. This is now the base class of the strategy design pattern. And this I can implement this in various ways. Shape actually doesn't have to change. The derived classes change a little bit. In addition to the other data members, they now, for instance, in the constructor, take a pointer to a draw strategy. This draw strategy is first of all moved into the data member. I own the strategy now, and whenever somebody calls draw, I simply forward the draw request to my draw strategy. So I no longer have to deal with implementation details. I can forward this request to some other implementation. The idea is sound. Although, of course, I introduce a second virtual function, which is something that we should think about. But there is a problem with regard to the interface segregation principle. For some reason, we have the tendency to put all things that are named similarly together in a class. So like here, I have two draw functions. I put both of them in the draw strategy. That is a violation of interface segregation. Think about it. What happens if I add another draw function? So for instance, a draw function for a rectangle. Well, then both circle and also square and all the other shapes that already know about the strategy would see the change. And for that reason, might have to recompile again and might have to change again. And in other words, there is coupling, unfortunate coupling, because I put these two functions together. The right solution, the solution according to the interface segregation principle, is to have a draw strategy for every single kind of shape. So there is probably a draw circle strategy. There's a draw square strategy. And with every new shape that I introduce, I additionally introduce a new strategy. Although this is, of course, a proliferation of base classes, it still is exactly the right thing to do in order to cut dependencies. This is pretty important to keep things under control and to not couple artificially. This is truly artificial coupling, nothing more. So, of course, this is just to sum this up. Circle does now get the draw circle strategy and stores it accordingly. And square gets the draw square strategy. Now, every shape only knows about the strategy that it truly needs to know about. Again, interface segregation is not just for class hierarchies. So it's not just for OO programming. We can also apply this to generic code. And again, it's centered around the concepts. Ultimately, concepts are the template equivalent of base classes. They are a set of requirements. If this set of requirements is kept at a minimum, copy actually follows this interface segregation principle also. So this copy function only requires an input iterator and not something that is much more demanding. And it also only requires an output iterator, minimum requirements for this particular function. And so I have minimum requirements in total. This is why copy works together with files, with virtually anything. If I would choose different kinds of iterators, I might actually restrict the uses. So interface segregation applied to concepts. The takeaway here is that make sure interfaces don't induce unnecessary dependencies. Make sure that you do not artificially couple things together. It is, however, to some extent, a special case of the single responsibility principle. So if you try to adhere to that, you might automatically, perhaps accidentally, also deal with the interface segregation principle. It is a special but important case. Now, this was the fourth one of the solid principles. There's only one more to go, which is unfortunately a little more complex. And now means that we have a little excursion into architecture as well. So the fifth of these principles is called Dependency Inversion Principle. Robert Martin tried to explain it like this. The Dependency Inversion Principle, short DIP, tells us that the most flexible systems are those in which source code dependencies refer only to abstractions, not to concretions. And he refined the statement with the following two rules. High-level modules should not depend on low-level modules. Both should depend on abstractions. And abstractions should not depend on details. Details should depend on abstractions. So this is very abstract in itself. So allow me to explain by means of an example. So for a long time, so for the entire time so far, we have dealt with drawing circles. Now let's try to refactor all this stuff. Drawing is now a completely separate aspect in a different component. So in the drawing component, I deal with drawing, whereas the geometry component contains circles, squares, and all the other geometric primitives. I now assume that the geometric primitives are a little more close to the center of my architecture. So this is why I call this high level. Drawing, however, is something that is a little more outside of the center. So this is something where I, for instance, might to introduce new ways of drawing things. This is why I expect more change. So this is more low level. In this setting, however, things do not work well. Circle now directly depends on draw circle. Draw circle being the implementation of drawing a circle. If that truly is the case, then circle might change often. It might change whenever draw circle changes. And that is exactly what I would like to avoid. I do not want to change the high-level stuff often, and I definitely do not want it to depend on the low-level details. For that reason, it is always recommended to introduce some kind of abstraction. And we now do this again in terms of a base class. This has a couple of very positive side effects. First of all, I do not depend on the implementation details anymore. Second, of course, now I'm able to introduce different kinds of drawing easily. The circle only depends on this abstraction. And indeed, I have some kind of local inversion of dependencies because the error, the direction of this error has reversed, has been inverted. Unfortunately, many explanations of the dependency inversion principle stop at this point. Right now, we did not really fix our architecture. Still, the high level depends on low level details. So circle depends, and I said this explicitly before, on this interface. If I really want to have a proper architecture, if I really want to have proper dependencies, then this is not what really works. I have to make one more very, very important and decisive change. I have to move the interface from the right side to the left side. This may seem like a trivial thing to do in a first glance, because structurally nothing changed, but architecturally this is a fundamental change. I no longer have an arrow pointing from left to right. Now the arrow really points from right to left. And it's no coincidence that UML uses this arrow. It points towards the base class. The change is a big one. Now circle doesn't depend on this interface anymore. It owns the interface. Circle itself specifies what it needs in order to draw itself. So circle owns it and can change it at any time. Draw circle, the implementation now depends on this interface. It has to implement it based on the requirements that circle and probably all the other shapes pose. So I have truly inverted the dependency. And only to do that little change, moving the interface on the left-hand side, I can now add a lot of different kinds of implementation on the right-hand side without having to change the left-hand side. The higher level now no longer depends on the details. That is true dependency inversion. That is actually pretty important. If you really think bigger, think about architecture. And for that reason, I have a slightly bigger example. I wanted to show you a model view controller. I know there is a lot of different names and ideas what a model view controller is. So I stick to the definition given in Wikipedia. So a model view controller is 3 components that work together. There is a controller that gives some kind of input, which is forwarded to a model. The model is supposed to contain the business logic, the things that should change as rarely as possible, but gives an answer to this input and passes this on to a view, any kind of view. Right? You could imagine some screen, a terminal, anything. Architecturally, this is where I would draw an architectural boundary. The model should be part of the high level, truly at the top, high, controllers and views should be at the bottom, because I can imagine that I can add many, many different controllers, many kinds of views, but I probably will not change my model very often. This, however, only works if I really think hard about my dependencies. If these errors, as I have them right now, are the dependencies, then I have a broken architecture. What I truly need is a dependency from controller to model and from view to model. And so, especially in the right-hand side, I truly have an inversion of dependencies. And I achieve this by having the interfaces on the model side. Model, again, defines itself how to deal with controllers, how to deal with views. And this allows even third-party people to add new kinds of controllers and new kinds of views without the model having to change. So true dependency inversion. Again, I started with inheritance hierarchies, but again, you can apply this to templated code as well. And for the fourth time, I now use the copy function. Simply, it really works also here. And again, it is about the concepts. Concepts, just as base classes, represent a set of requirements, a set of specifications, which function you should provide and how they should work. If you pass me an input iterator that supports comparison, that supports increment, that supports dereference, and where I can read from the dereference thing, then you can use copy. However, copy doesn't rely on you to do the right thing in the sense that it owns its concept. It itself specifies what operations are required. And so, interestingly, copy is implemented in terms of these requirements. And interestingly, this is why you depend on copy. Copy doesn't depend on you. You have to follow the rules that copy lays out for you, else it just doesn't work. This is why you depend on the standard library and not the standard library on you. This is why the standard library is not at the bottom of your architecture, but usually pretty high. You depend on this essentially everywhere. And of course, this is a very clever and a very correct way to implement a standard library. So the takeaway here is to prefer to depend on abstractions, whether this is abstract classes or concepts, instead of a concrete type. This enables you to protect yourself against changes that happen often, but it only works if you truly think about where the abstractions should be. So a fundamental question of this dependency inversion principle is, where does the abstraction belong to? So this was now almost 60 minutes about the solid principles. So we've talked about each of these ones, and hopefully I could show you that all of them somehow deal with dependencies in your code. So to summarize, first of all, the solid principle are more than just a set of OO guidelines. I believe they're truly a universal set of guidelines that helps you with any kind of coupling. So this use the solid principles to reduce coupling and facilitate change. If you follow them, you should have a much, much easier time to change things, to extend things, and to deal with dependencies. The single responsibility principle helps you to isolate changes. That is definitely something very, very valuable. The open-close principle, however, helps you to add things, to extend things more easily. That, of course, is also pretty important for long-term maintenance. The iskov substitution principle is about what is a good abstraction, what is not. So it tells you how to write abstractions in the first place. The interface segregation principle is about minimizing dependencies in interfaces, which, as I said, is a special case of SRP, but a really important special case. And the dependency inversion principle helps you to steer dependencies in a specific direction. Only that truly enables you to modularize things and to separate things on a bigger scale. Although, of course, you've seen with copy, it definitely also works on a small scale. With that, I'm very happy to take a couple of questions if there have been a couple. So there was a question. I probably have to read it. So for open closed, you're saying you have to choose which is a priority, optimize for new types versus new operations. Yes, unfortunately. So as long as you want dynamic polymorphism, you indeed have to choose what is more important to you. Even modern schemes like using standard variant, which allows you to add operations really easy, or something like type erasure, which allows you to add types really conveniently. In all of these approaches, still, you have to favor one over the other. So I am not aware of any solution that allows you to very easily add operations and types in dynamic polymorphism. Static polymorphism is easy in this case, but still, you may be restricted depending on what your design truly is. However, it is important to keep in mind that there is these two dimensions of OCP. It's not just the one thing you primarily think about adding types, it's also about adding operations. Okay, question 2. For the iskov substitution principle, in my square rectangle example, the better choice is to have square and rectangle as two separate classes that don't inherit? Absolutely. Strictly speaking, it depends on how you implement your two setters. If you do have two setters, if you do have set width and set height separately, it will not work in an inheritance relationship. You cannot uphold the invariance of the base class. If you have a set both function, and I cannot think of a better name right now, so a function that allows you to give both height and width, then this is an awkward interface for square. But this might work. But since it's awkward, I would also not go there. If you don't have any setters, you could use it, but then it's very inflexible. I would truly prefer to not have square and rectangle have a relation. One of the things that you might think of is a shape-based class that does not have any, where you don't have any expectations on the form or properties of the driving class. So perhaps square and rectangle in computer science simply do not have anything to do with each other. Okay, now question 3. About the iskov substitution principle again, does something like a polygon interface with get area and get perimeter solve the problem? Get perimeter. So I probably have to think about this too. It might. It totally might. My personal preference, however, is to try to separate concerns as much as possible. So LSP is tricky. Also, I don't want to run into subtle problems later. So I tend to argue the less coupling, the better. So perhaps this approach works, perhaps it doesn't. Okay, I hope this was helpful for you. Thank you very much for attending.